Hello, everybody. I'm Otto, and I'm here with the whole group that's behind DyVE, the framework for value dynamics. So Jan, he will continue in the talk, and Sean and Tenchi. We call ourselves decision science. We are part of a data science department aligned with Merck Research Laboratories. And we have a big vision to make a big change in a big company. Merck invents and produces medicines for human and animal use. And it's a very high stakes gamble that you have to brace yourself for spending over $10 billion over 10 years of time and having a failure rate around 95%. So most of the projects fail in the biology research or chemistry or pharmacology, or they are not efficient enough or for other strategic reasons. So it's a zoo, and the whole process of discovering and developing new medicines is very complex because of the variety, dynamicity, all kinds of uncertainties, also because of human decision makers who are not really well coordinated, and because of outside factors. So what we want is to improve the productivity of R&D productively. And for that, we use scientific machine learning, obviously, Julia. And we have to deal with a large variety of processes at many scales, starting from the molecular over research processes, clinical trials, manufacturing, up to public health. And for that, we've chosen a small number of key abstractions that we use and augment and integrate. So that would be chemical reactions or generalized chemical reactions as Petri nets, and notably open Petri nets, but we also extend them. We allow for non-integer coefficients. We allow for delays. We allow for capacity constraints on the transitions, callbacks, of course. On the production side, you can produce actions that are like small scripts that rewrite the state. And the state, microstate and macrostates, can be anything representable in a computer. And the resources, so that generalize the chemical species, the resources may be physical, like biological material or chemical material. It can be human labor, it can be information, it can be money, it can be contracts. And to get a better view, we represent things hierarchically. For that, the resource and process algebra of operands, or the applied category theory is again a great abstraction for us, but we also use data structures and functions from algebraic Julia, the computational applied category theory ecosystem. And when we simulate, we mostly, this is mostly but not exclusively metaprogramming, that from a high-level specification language, DyVE, we generate problem specifications in differential equations.jl as discrete problems. But we can then simulate or co-integrate those with problems in differential equations proper, or agents.jl, or algebraic dynamics. And not to disclose any trade secrets, but we had to apply this. We developed the framework. 3 packages are open source on Julia GitHub, and the 4th is in the process of being put there. And the 2 key are reactive dynamics, that's the chemical network generalization, and algebraic agents, where you can have a hierarchy of spaces and agency, and they are coordinated, and you can also link the 2 together and orchestrate co-integration with external things. So the 3 applications in-house, one was in systems pharmacology. So this is all about dynamics on networks of relationships and values. And at the finest granularity, the network was a network of reactions and relationships between molecules in the brain, and the decision variables were about 1,000 variables. When you would be adding some combination of candidate drugs, and you look to maximize the effect but minimize the overall dose. With the same approach and tool stack, we also optimize networks of, or experimental design in preclinical, where you have a good biological and chemical hypothesis, how you want to do something in the body. But before you can try doing that in even healthy volunteers in clinical trials, you have to do a battery of different tests in preclinical. They can be in silico, in vitro, in vivo, and it's a big network. And we help the projects navigate the network by choosing the next best experiment, which would decrease uncertainty about key questions in preclinical, but also would save time and money. So of the local value surrogates like speed, quality, cost, capacity, we add also information gain. And as we can integrate models algebraically, we can also have generative models that are coherent because they represent a joint distribution over many things at different scales, and that would increase the coherence of decisions. So, and I didn't mention the third application in supply chain optimization. So when you plan for a new clinical trial, you have to make sure that you manufacture in time enough of the new substance and you distribute it. It can be to a large number of countries globally, and some of the distribution chains have to be cold if these are vaccines, for example, and controlled and so on. So this is just to illustrate that we can and do apply the approach at different scales. Yeah. Okay, I will skip the large process model, which was really a synthetic. It was not an application for Merck research labs, but just to show that we could build a synthetic model of the whole life cycle of the whole company, and with the hope that if anybody wants to use it for real, they would just focus on a domain and replace the synthetic input data with their own data, and with a codeless or code-free approach, they would have a digital twin of their domain. So I invite Jan to continue in the detail, and all the most of the development
Hello everyone, I'm Jan. I'm a research scientist in AutoSteam, and I've been the main developer of the 3 packages and some other packages which are due to be published very soon for over the last 3 years. And as we heard, our credo is to approach the task of process modeling productively. And to achieve this goal, it has been a long-standing challenge for us to properly define a framework of the process models that would be able to capture a wide range of different processes that occur in science or in business, and at the same time like to keep this framework manageable and tamed so that it could be really maintained and people could onboard this framework quickly. So of course, the key idea is that many different problems can be tackled using some very specific packages. So, for example, how to model the chemical reactions, you can use Catalyst, or there are some you can use agents for some agent-based modeling. But we would like to provide some or define some framework which is able to accommodate all or a wide range or a broad range of these problems, so that the models would be interoperable, and we would need to spend much time trying to bind these different pieces together. So this is a very it's the main feature or the main goal that we are trying to pursue. So the starting point for us for the framework was in the category of open pattern net. So I'm not sure whether we are familiar with this concept, but you can think of this as some that we have some 2 types of objects. So we have some agents or some entities, and we have some rules that move these agents or these entities in the system. That are these transitions or these rules are the driving force of the system. And already pattern nets are very powerful, but of course they are not able to to capture all the complexity of the processes that naturally occur in science and business. So this generalization took part in several steps. So first, we wanted to make the agents or the entities more granular. So the entities can be thought of as some generalized agents which are structured, which have their own identity. And then the transitions or the rules that move these agents, these entities, can have some further attributes. So, for example, the duration of the transition, or some maximum number of the transitions occurring in some time unit, or some cost which is incurred by the transition, and so on. So this is so we relate to DyVE by extending or enlarging or enriching the category of pattern nets. So that's for two main. These are 2 main take points for this. And the another one is that we want to make possible to to easily compose different process models into a compound process model, and also and this is somehow hidden this in the figure, but we try to make it easy to define these networks. So to this purpose, we developed some domain-specific language which can be used to set up the transitions and define the agents in the process models. So even we have no doubt that all these features are truly revolutionary. The development of this package called reactive dynamics took place in several evolutionary steps. So we already started with the pattern nets, where there's some every transition has some left-hand side, some right-hand side. There are tokens or entities that are moved by these transitions, and then we are iteratively adding some attributes to the transition. So, for example, the duration of the transition, some intensity of some working number of the transitions that are spawned in time unit, and also some probabilities of the successful of the transition being terminated successfully, and so on. And so this is really some iterative process, and ultimately we are trying to to model even the transitions as some kind of generalized agents, so that a transition could occur, for example, on the left-hand side of another transition, and this would open the way towards, say, a structured transitions or so. So the modeling process in interactive dynamics takes in several different steps. So the first step is that you have some mental model of some process model of some you have some reactions, and you specify this, or you define your state, this mental model, using the domain-specific language of DyVE. So this really resembles the syntax of, for example, catalyst, or some battery nets. So you need to provide the intensity of the transition at the left-hand side, the right-hand side, and you can also provide the further attributes of the transition. Yeah, that's shown on the right-hand side. Then this information, this definition of the process network is stored using so-called ACHET. So if you are familiar with GATLAB and ACT, you will know what I'm speaking about. But you can think of this as some very tricky database which allows for simple handling of querying the data which is stored in the database, and then we take this database or the problem specification, turn this into some problem that can be really simulated or evolved. And with interactive dynamics, this problem is a very particular problem. It's a discrete problem within differential equations package, and this is very powerful because you can then very easily do any sort of optimization tasks, or you can perform some ensemble analysis, parameter fitting, or so. And we also to simplify this even further, we also develop some macros that can be used, for example, just for plotting or for simulation of the system. So you don't need, or some scientist doesn't really need to learn how to work with differential equations, but can use instead a set of, let's say, 3 or 4 macro constructs which export most of the functionality of say differential equations. Yeah. So this on the right-hand side, you can see how we pass from the database to the differential equations problem, and then we can perform, say, some simulation or some ensemble analysis. This is shown on this slide. Okay, and there's another package or another say initiative within the DyVE framework, and yeah, as I mentioned, or you may have noticed, very often I use the word agents. So it's very comfortable for us to think of the different entities, within the networks or the particles, as of some agents. And we developed a package which allows you to very efficiently structure some agent models. And so, for example, you know that, for example, in agents, as far as I know, the agents are indexed by integers or so, and they are all, say, within the same flat hierarchy. But so this is great for some particle swarms or so, but in for some more practical applications, for example, in science and business, it's very natural to structure the agents into some hierarchies. So, for example, as you can see, on the the tree somehow depicts some hierarchy of agents where we can structure, for example, the pharma company into different areas, into different departments, and there's some department for production, and this department has some embedded agents, and something similar is, for example, for logistics and for market, and all these agents can be or entities can be structured or can be put into this single hierarchy. And it's also very easy to query this hierarchy and to for example, to index different agents within the hierarchy using some paths and using relative paths, really like in a Unix file system. So this is very powerful to reference the different agents within the hierarchy. And another feature of this package, and I would say this is really some killer application, which makes the package very different from, the usual agent-based or other packages that are for the purpose of agent-based modeling. That we try to make possible to co-simulate or to co-integrate different kind of dynamical system or the modality. So in case you attended yesterday's lecture on neural DE about the FMIs, FMUs, you will this will definitely ring many bells with you. But I would say that we try to avoid the complexity, the heavy machinery of MAIs, MMUs, and instead to develop some really lightweight interface that allows you to wrap different dynamical systems which were defined in different modalities, for example, some discrete time agents or some differential continuous time differential equations problem. You can then wrap all these different kinds of problems into a single hierarchy, into a single system. And how this is done? So, somehow assume that all the agents, the different dynamical system within the hierarchy, they share some kind of implicit global time horizon, or and we make it possible for each agent to have its own evolutionary rule, and also the agents somehow export the time when they awake, or when they wake up, and when they proceed to the next state. So, this is actually, it may seem quite complex, but it's very easy, and it's really, if you have for example, some differential equations problem defined in DyVE, you just need to provide some wrapper function which wraps the integrator of the DyVE problem, and you specialize a set of common interface methods which were defined within this algebraic agents package. And it's even more simple because we know or we tried to, or we prepared some wrappers for several very popular packages. For example, the differential equations for agents or for algebraic dynamics, so that if in the case that you have some continuous time problem defined in DyVE, or some discrete time agent-based model defined in agents, you can simply use the provided functions which will wrap these different models as the algebraic agents, and then you can put these different agents into a single hierarchy, and then you can co-simulate or approximate the joint evolution of the system. So it's very important to know that that we don't really claim to have some to be able to get the exact or the most exact approximation of the joint dynamics. Instead, we are trying to balance the costs of developing some fine-grained model on the one hand, and on the other hand, the accuracy of this of the resulting of the results of the simulation results. So, and usually, and we are testing this medicine on ourselves, it's enough really to get some fast approximations as far as they can be developed very quickly, and then based on the preliminary results, you can then invest into some more very granular models of the dynamics. But really, we try to simplify the process of approximating the dynamical systems and putting different systems together. Yeah, because often in practice, for example, as we try to optimize some process in the pharma company, there are already available models, for example, for logistics, for production, and the optimization takes place well separately or in some sequential manner. And already by trying to establish some weak links between these different models can really prove advantageous and can open some way towards stepping some new value and optimizing both the business and research processes. And this is what we are doing at now, the Decision Science Group with Otto. Thank you.
Do we have questions?
I have a very pragmatic question. So if folks have more technical questions, perhaps that would be more broad interest. But I'm just wondering how you communicate the value of these systems to folks who are less familiar with applied category theory.
We don't mention category theory at all. And we don't mention Julia too much. We started. Now there are more Julia users at Merck, but it's still a very small community. Yeah. But we use the diagrams, and we use the power and speed so that we can do not just local optimization or to have some results, but to show the big picture, to construct palette of frontiers for decision problems where you can show not what's the best decision, but if you have, say, almost best, you can save a lot of resource or time and so on.
Thank you very much for that talk. Otto, you had mentioned that optimal experimental design is one of your applications. I was wondering if you could say a bit more about what you're doing about that.
Yes, it's an example. So you have, let's say, a small molecule, and you want to establish how safe it is, and the, say, pharmacokinetics, pharmacodynamics, and other, or whether it gets into the brain, for example. So for these domains, you can either statistically choose that you would start with experiments that filter the most, because you don't want to do a lot of stuff with compounds that you abandon eventually. So you want to filter, and you want to start with experiments which are fast and cheap, and leave those where, say, in vivo expensive experiments for the end. But you can improve on that adaptively. If you have a history of compounds, you would say you can explore the tree, how you would go in sequence of experiments, and how you would decrease the information entropy of the results using the historic data as a proxy for the information gain approximation. And you get the bookkeeping, you know how much time and money you would spend for that. So this is a stochastic, a Markov tree search. And in this, you can combine machine learning and the simulation of the projects as Petrinets, that you would, the callback would call the machine learning piece, the Bayesian dynamic programming algorithm, to recommend the next best experiment. You go there using the dynamics, and you can also simulate the context, other projects competing for your resources. And then based on the outcome of the experiment, which you get from the real world, you then condition the other learning. So it is very, well, adaptive, customized for your project. If that is an answer to your question.
Yeah, separate package for this purpose. Exactly, it will be out in, say, 3 or 4 weeks.
Yeah. But you can use it, for example, for patients in ER where the experiments would be diagnoses. And
yeah. Hey, Otto, one quick question here. Yeah, so normally when I've seen it in the QSP context and such, right, a lot of people are doing the ODE models. I haven't seen too much use of the Gillespie processes and the discrete time processes. Wondering if you could describe how much that's used within Merck, and what kinds of things the stochastic modeling is interesting for.
Well, we are not pharmacologists, even though Tenchi has most of, well, yeah, he would be, but he joined only earlier this year. And so we made the jump from systems biology, from using Petri nets and the ODE models to represent the pathways in R&D, where you consume, well, you don't take chemical species, but you consume human labor, money, and material, and so on. And there you would have statistics, say, for a project of this type at this stage, what is, say, the duration and attrition rate and cost and so on. So this is where you get the stochasticity.
Let's thank all our speakers from this session again.